So in this video, we want to look at the cotangent function and identify why it looks the way that it does. But we're going to start out by looking at the tangent function, which we've already defined in a previous video. So here's a graph of the tangent function. Here's some of its vertical asymptotes. The tangent function we want to remember was defined as y over x. Tangent of theta equals the ratio y over x on the unit circle. So if we're sitting on the unit circle, we have for any ordered pair xy, the tangent of the angle is just the ratio y over x, and the cotangent function is just the reciprocal of the tangent function. So the tangent of theta is y over x, and the cotangent of theta is x over y, or in other words, the cotangent is just 1 over the tangent function, tangent of theta. So let's look at the vertical asymptotes on the tangent function and ask ourselves, how did we get those? Well, we got those vertical asymptotes whenever the tangent function was undefined, and that happened whenever x was equal to 0, and x was equal to 0 every 180 degrees. So x was equal to 0 here, and x is equal to 0 right here. And anytime x was equal to 0, we got an undefined tangent function. But now with the cotangent function, whenever x is equal to 0, x will be in the numerator, and we're going to wind up with the ratio 0 over plus or minus 1 on those quadrantal angles that are coterminal with 90 degrees and 270 degrees. So the gist of it is that every time the tangent function has a vertical asymptote, which meant we had division by 0 or 0 in the denominator, that means that the cotangent function is going to have a 0 in the numerator, and the cotangent function will equal 0. So these vertical asymptotes on the tangent function will correspond to zeros on the cotangent function. Now we want to look at the tangent function. Here's the tangent function, and think about, well, why did it get zeros where it did? Here are the zeros of the tangent function, the places where it's crossing the theta axis. Well, those zeros happened when y was equal to 0. We would get 0 divided by plus or minus 1 is 0, and the tangent function would get a 0 at those spots. But now whenever y is 0, y is now for the cotangent function going to be in the denominator. So we'll have a division by 0, which means that the zeros of the tangent function will be the vertical asymptotes. So here's a 0 of the tangent function, but that's going to be a vertical asymptote for the cotangent function because of their reciprocal relationship. So here's a 0 on the tangent. That's going to be a vertical asymptote on its reciprocal function, the cotangent function. So we'll just draw a few of these in. Here's a 0. Here's a vertical asymptote. We'll draw 2 more in. I know it's time consuming, but we have all the time in the world. Here's a 0. Here's a vertical asymptote. Here's a 0 on the tangent function, so we get a vertical asymptote on the cotangent function. So now we want to think about when we have a reciprocal. Does reciprocating something change the sign? And the answer is no. So for what I mean by that is if the ratio x divided by y is positive, then the ratio x divided by y is positive. Doing the reciprocal doesn't change the sign of a number. If I have positive 3/2 and I write its reciprocal, it will still be positive. If I have negative 3/2, its reciprocal will still be negative. So the next thing I can go is look between my asymptotes here. Here's the tangent function. So if the tangent function is positive, the cotangent function, which is just the reciprocal of the tangent, will have to be positive. Here the tangent function is negative, between this 0 and this vertical asymptote. So the cotangent function will need to be negative. Tangent function positive means cotangent positive because they're just reciprocals. So the cotangent function is going to alternate signs, positive, negative, positive, negative, in exactly the same way that the tangent function did. And then that then allows us to really draw the graph fairly easily. So the cotangent function's positive means it's going to be sweeping along in the positive world along its asymptote. It's going to come to its 0, pass through it, and it's going to be negative in the same places that the tangent function was negative, sweeping along its asymptote. So it's going to come in, pass through its 0. So we really get the look that we do because we're just the reciprocal of the tangent function. So it's going to have this basic shape. So wiping out my bad drawings, clear my bad drawings, and take away the tangent function, and we'll graph the cotangent function with its asymptotes. And they're going to be located just the same way that we drew them. So we want to think about some additional key features. So the tangent function had some key features, and it's going to turn out that the cotangent function will share those same key features. So on the unit circle, with the tangent function, it was important that we looked at the 45-degree angle, or pi over 4 radians. And the reason this was a good point for graphing was the x and the y coordinates are the same, root 2 over 2, comma, root 2 over 2. So for the cotangent function, if we're taking the ratio x over y, we're just going to get a 1 at 45 degrees. Root 2 over 2 divided by root 2 over 2 is 1. So between 0 degrees and 180 degrees, or 0 radians and pi radians, we have our 0, which is pi over 2, or 90 degrees. And halfway between 0 and 90 degrees is our 45-degree angle, or pi over 4 radians. And just like with the tangent function, that point is going to be pi over 4, input 45-degree angle, output will be a 1. And if we reflect our 45-degree angle over into quadrant 2, because here we're moving from 0 to 180 degrees, halfway between 90 degrees and 180 degrees, there will be a 135-degree angle, or 3 pi over 4 rads. That's going to be this angle right here, 135 degrees, which is the reflection of the 45-degree angle in the line, in the y-axis. And the ordered pair here is now going to be negative root 2 over 2. Root 2 over 2. So when we take the ratio x over y, we're going to get a negative 1. So we wind up with this nice point on the graph, 3 pi over 4, comma, negative 1. And these are going to be key points for graphing. So for the cotangent function, knowing the location of the first two vertical asymptotes at 0 degrees and 180 degrees, or 0 and pi radians, is important. Knowing that the 0 of the function is halfway between them, knowing that between those two we cut it into quarters, and that at the quarter marks we get the key points where we output a 1 and a negative 1. That's important when we're doing vertical stretching. And it's important to know that the period is 180 degrees, just like for the tangent function, or pi radians. So we're going to get, for one period, we're going to get 3 key points on the graph, plus our 2 key vertical asymptotes. And that will be the tools that we use for graphing the cotangent function. So the only thing left to really discuss is domain, range. We've already talked about period, but we'll talk about it one more time. And again, we can't input values, angles. We can't input angles theta that will generate zeros for the x's, and we know that occurs at when y is equal to 0, because the cotangent is the ratio x over y. So whenever y is 0, which on the unit circle happens here, at 0 degrees. We get 1 and y is 0. So we get division by 0 there. And it happens here at -1, 0, which is 180 degrees out. And every rotation by 180 degrees from there brings us back to y equaling 0 again. So it's easier to say, we can't have division by 0, so for the domain it's easier to say what we can't do. Don't let theta be any integer multiple of 180 degrees. Otherwise you're going to land on a spot that has y equal to 0. So where k is an integer, don't do that. And in radian world, that would mean don't let theta be any integer multiple of pi radians. So we could also identify this from a radian perspective by saying don't let the angle be an integer multiple of pi radians, or y will equal 0, and the cotangent function will have division by 0 and be undefined. The range is going to be the same as it is for the tangent function. Our function values f of theta can range from, hey, the function goes to -infinity, and the function goes up in the positive direction to positive infinity. So the function values are going to range from -infinity to infinity, and the period is going to be 180 degrees or pi radians, because between every two vertical asymptotes the function completely repeats itself, and those vertical asymptotes are 180 degrees or pi radians apart. So that's the key features of this cotangent function.